I am going to explain chapter 4 in the course Chemistry 101. Chapter 4 is about chemical bonding and chemical reactions. First, I'm going to talk about reactions, stoichiometry, and I'm going to give an example about this topic. This example is in the book, example 4.1, page 83. It says that we had a reaction, carbon dioxide with water, in presence of sunlight. It yields oxygen gas and glucose. They mentioned that we have in the reaction 37.8 grams, and we need to know how many grams of glucose is produced. So we start. The reaction is, we say here we have 6 moles of CO2. Before converting the reaction in moles, and we have first to convert the grams to moles. We have to convert the grams to moles, then after that we get the glucose in moles, then we convert the moles of glucose to grams. So we say we have to convert this mass to moles by dividing it to its molar mass. Its molar mass, 44 grams per mole. Because carbon is 12 and oxygen is 16, so the total is 44. And this, we calculated, it is equal to 0.859 mole. Now we have 6 moles of carbon dioxide. This produces 1 mole glucose. But we have in the reaction 0.859 mole. And this gives X mole of CO2. This X is equal to 0.859 times 1 divided by 6. And this is equal to 0.143 mole glucose, C6H12O6. And now we need to convert moles to grams into grams. So we say we multiply the moles by molar mass. So mass is equal to number of moles, 0.143 mole, times the molar mass of glucose is 80 grams per mole. 180 grams. 180 grams per mole. So times 180 grams per mole. And this is equal to 25.8 grams. Now we'll talk about limiting reaction. Theoretical yield and percent yield. Limiting reactant is the reactant that is completely consumed in a reaction and limits the amount of theoretical yield. So limiting reactant is consumed completely in the reaction, and there is the amount of product level. And we have also the reactant in excess. The reactant in excess it is any reactant that occurs in a quantity greater than is required to completely react with the limiting reactant. And we have the theoretical yield. The theoretical yield and that is another yield, is the amount of product can be made based on the limiting reactant, based on the amount of limiting reactant. Here I would like to give an example about this topic. Page number 86. We have a chemical reaction, 2NO, nitrogen monoxide, plus hydrogen, yields ammonia, plus water. And it says we have 86.3 grams, 86.3 grams nitrogen monoxide, and 25.6 grams of hydrogen react to produce ammonia. And we need to find the theoretical yield. And then find the theoretical yield. Right, so another. So we need to find the theoretical yield of ammonia in grams. So same thing here, we have to convert the mass into moles, grams into moles, by dividing it to a smaller mass. The nitrogen is 14, the oxygen, the molar mass of oxygen is 16, the total is 30. So 86.3 divided by 30 gram per mole. And here 25.6 divided by 2 gram per mole, and this is equal to 12.673 mole, and this is equal to 2.876 mole. So now we have in the reaction 2 moles of nitrogen monoxide. We need to calculate the theoretical yield, or we need to calculate the nitrogen monoxide, how many moles produces ammonia, and same thing to calculate how much the hydrogen gives us, how many moles of ammonia, to determine the limiting reactant. So now we calculate based on NO. We have 2 moles of NO. Gives us 2 moles of ammonia. But here we have the reaction 2.876 mole nitrogen monoxide. And this gives us X, which we need to calculate. Of course, since 2 mole gives 2 mole, so 2.876, it will give same 2.876 mole ammonia. Now we calculate it for hydrogen. We have 5 moles of hydrogen. Five moles of hydrogen gives us 2 moles of ammonia. But we have in the reaction 12.673 moles hydrogen, and this gives us X equals to 12.673 times 2 all divided by 5. And we calculate it from the calculator, which is equal to 5.69 mole of ammonia. So here we see the nitrogen monoxide gave us 2.876 mole of ammonia, whereas the hydrogen gave us 5.69 mole ammonia. So the list number is 2.876 number, 2.876. So the limiting reactant is nitrogen monoxide, and the theoretical yield will be 2.876 mole equals 2.876 mole of ammonia, but we need to convert this moles into grams, so we will multiply it by its molar mass. So the mass is equal to 2.876 times nitrogen we have 14 and each hydrogen 1, so the total is 17 times 17 gram per mole, and this is equal to 49, about 49 grams. Now to cover this subject, I will add one more question to this example. The question is, what would be the percent yield if the reaction produced 40 grams of ammonia. So here that means the actual yield is equal to 40 grams, and we have the theoretical yield 49 grams, so the percent yield is equal to actual yield divided by theoretical yield, and this is all multiplied by 100%. Actual yield is 40 divided by critical yield 49 grams times 100%, and this is equal to 81.6%. Now I'll talk about solution concentration and solution stoichiometry. Solution concentration which means its molarity, and it is expressed with the equation molarity, its symbol M, is equal to number of moles of solute, number of moles of solute, المادة المذابة, divided by the volume of the solution in liters. Actually, here we can draw this triangle. We put moles on the top, and we put M molarity and V in the bottom of the triangle. So if you want the molarity, it's equal to moles over volume. And if you want volume, it is number of moles over molarity. And if we need moles, it is equal to molarity times volume. Here I'll give one example. If 20 grams of an sodium hydroxide, 20 grams of sodium hydroxide, dissolve to طيبة in enough water to make 300 milliliters of solution. What is the molarity of the solution Here we see the equation is in moles, the solute in moles, and we have it here in grams. So we need to convert it into moles by dividing it on its molar mass. So we have 20 grams, so number of moles equals the mass, 20 grams, divided by molar mass, in here OH. Sodium we have 23 gram per mole, oxygen 16, and hydrogen 1 gram per mole. So the total is 30 grams per mole. And this is equal to 0.5 mole. Also, we have the volume of the solution, 300 milliliters. must be given in liters. So we need to convert it to liters, and this is equal to divided by 1000, and this is equal to 0.3 liters. Now we can use the equation M equals number of moles, we have 0.5 mole divided by the volume of the solution is 0.3 liter, and this is equal to 1.67 m molar. And this is expressed in the equation M1 V1 times equals to M2 V2. M1 V1 is molarity and the volume of the stock solution, المحلول المخزن, which is concentrated solution, and M2 V2 is the molarity and volume for the final solution. So I'll give an example. The final molarity of HCl, hydrochloric acid, if 25 milliliters of 4 molar KH2PO4 was diluted to a final volume of 0.5 liter, would be so we have the information from this question, 25 milliliter, which is V1, 25 milliliter, and its molarity of the solution, which is the stock solution, V1 we have here 4 molar, M1 4 molar of 4 molar, KH2PO4, sorry I forgot to put 4 molar. So we have V1 25 milliliters and M1 is equal to 4 molar, and we have the final volume 0.5 liter, which is V2, 0.5 liter, and into the final molarity, which we need to calculate, is unknown. Here, as we see in this question, the volume 1 is given in milliliters and volume 2 in liters. So actually, if we either we have to put both in milliliters in the equation or both liters. So we'll convert the liters into milliliters. We multiply it by 1000, and this is equal to 500 milliliters. So now we can use the equation M1V1 equals M2V2. M1, we have it 4 times V1, 25 milliliters, equals M2, that we need to calculate, times V2, 500 ml. So M2 is equal to 4 times 25 divided by 500, which is equal to 100 over 500, and this is equal to 0.2 molar. Now I talk about types of aqueous solutions. Types of aqueous solutions. We have two familiar solutions, which are, the first solution is salt in water. Salt in water, and the other solution is sugar in water. And both of them dissolve in water very well. The first solution yields sodium ion plus Cl minus chloride ion, and the other solution in water, it will stay as it is, dissolved in water, but as intact. The difference between these two solutions, the sodium chloride dissipates or ionizes completely in water and gives cations and anions, positive and negative ions, whereas the glucose, the C12H2O11, the sugar stays that is intact as it is. So this solution conducts electricity, يوصل التيار الكهربائي, whereas this solution does not conduct electricity, لا يوصل التيار الكهربائي. So the solution that conducts electricity, we call it electrolyte. We call it electrolyte. So the electrolytes the solutions that are electrolytes are ionic compounds. As we see, sodium chloride is an ionic compound. And also, if we take the acid, HCl, in water, it will also ionize completely to H plus and Cl minus. So that means we have ionic acids and ionic compounds, we have ionic compounds and acids are electrolytes. and the solution that does not conduct electricity, we call it non-electrolyte. The electrolytes, there are strong electrolytes, which are ionic compounds, and strong acids. So strong electrolytes, ionic compounds, and strong acids. And we have also weak electrolytes. Weak electrolytes, they are weak acids. For example, we have hydrochloric acid in water. It ionizes partially, so we put two arrows in two directions, in opposite directions, to give H plus F minus. So the non-electrolytes, they are all molecular compounds. All molecular compounds, كل المركبات الجزيئية, except, as we see, the acids are also molecular compounds, so we say except ما عدا acids, which includes strong acids and weak acids. Strong acids and weak acids. Now let's talk about acid-base reactions. Acid-base reactions. We have three definitions for acid-base reactions. One of them is in this chapter, which is Arrhenius definition. According to Arrhenius definition, acid is any substance is a substance that produces H plus in an aqueous solution, and the base is any substance that produces OH minus hydroxide ion in an aqueous solution. Like, for example, HCl in aqueous solution, it gives H plus Cl minus. So, since it gives H plus, that means Cl is an acid, and NaOH yields in an aqueous solution Na plus OH minus. That means this produce OH minus. NaOH sodium hydroxide is NaS. And we have also fumic acid with base. This yields water and salt. For example, HCl plus NaOH yields water and NaCl, which is salt. This reaction is called acid-base reaction or neutralization reaction. This is called the neutralization reaction. For the acids like HCl, we call it monoprotic acid. Monoprotic acid. And for acids like H2 sulfuric acid, H2SO4, and H2CO3, we call them diprotic acids. And H3PO4, we call it triprotic acid. So, mono means أحادي, di means ثنائي, tri means ثلاثي. لأن أحادي البروتون, ثنائي البروتون, وحامل ثلاثي البروتون. Now I talk about oxidation reduction reactions. Which is called also redox reactions. Redox, the first three letters are ED, stands for reaction, and OX stands for oxidation. Oxidation means loss of electrons, فقط الكترونات. And reduction means gain of electrons. كسب الكترونات. So if we take a reaction, for example, Na plus Cl2 gives NaCl. NaCl. First, to determine the oxidation states for each atom, we have some rules for this. If the oxidation state of an atom in a free element is equal to 0, so here sodium, it's a free an atom, which is a free element, so its oxidation state is 0. Same thing, chlorine. It is the oxidation state of chlorine of chlor atom is 0. And the sodium here, which is in a compound. So we have some some rules for this. Group 1A, the oxidation state of group 1A is positive 1, 2A, positive 2. And aluminium in 3A, it is positive 3. And generally, the group 6A, the oxidation state of group 6A generally is negative 2, and 7A is negative 1. So here sodium, the total charge of sodium chloride is 0, and sodium is positive 1, and chloride, the chlorine atom is negative 1, the total must be 0. So we see here the sodium got oxidation, so it's oxidized, the sodium is oxidized. Cl is reduced, the chlorine is reduced. So we have here also another term, which is two terms. We have oxidizing agent, عامل oxide, and reducing agent, عامل مختزل. So the material which is oxidized, sodium, is considered as reducing agent. And the chlorine which is reduced, we consider it as oxidizing agent. Also, I can give some examples or some questions about the oxidation state. The oxidation state of nitrogen in NH3 and NO3 minus. First, we solve for NH3. So the total charge here is 0. Nitrogen, we put instead of nitrogen X, that we need to know to calculate. Hydrogen, we have 3 hydrogen atoms. Each hydrogen is positive 1 equals 0. So X equals negative 3. For NO3 minus, now we calculate it for NO3 minus. So the total charge here, as you see, is negative 1. So we put X plus 3 oxygen atoms, each has negative 2 charge, and this is equal to negative 1. So X plus negative 6 equals negative 1. That means X equals positive 5. I'll talk about types of chemical bonds. Types of chemical bonds. We have here in this chapter 3 types of bonds. The first one is ionic bond. Which is formed between metal and non-metal. The electrons in this type ionic, this ionic one is the electrons are, so it could be electron or more than electron. Electrons transfer. And the second type is covalent bond. It is formed between two nonmetals. And the electrons are shared. For example, for covalent bond, H2O, ionic bond, NaCl, and the third type is the metallic bond. Metallic bond, which is formed between metal and metal. So it is between or among metals. And the electrons in this type of bond, metallic bond, electrons are pooled. يعني الكترونات متجمعة. And it is pooled in electron C, تتجمع في بحر الإلكترونات, electron C. Now I talk about representing valence electrons with dots. Representing valence electrons with dots. Lewis structure. The electron configuration for oxygen, which has 8 electrons, is 1 S2, 2 S2, 2p4. So we see here that the valence electrons, or valence orbitals, 2s and 2p, they have 6 valence electrons. Those valence electrons, we can represent them with dots or Lewis structure. So only valence electrons that are represented. Oxygen has here 6 valence electrons, so we put 6 dots. So if I want to take more examples, in the group 1A, 2A, 3A, until 8A. We take lithium from group 1A, it has 1 valence electron. 2A, beryllium, it has 2 valence electrons. Boron from 3A, it has 3 valence electrons. And carbon in 4A, it has 4 valence electrons. And nitrogen in group 5A, it has 5 valence electrons. And in group 6A, we have oxygen, 6 valence electrons. And in group 7A, fluorine, it has 7 valence electrons. And neon in group 8A, it has 8 valence electrons. It is defined as the ability of an atom to attract electrons. If we take, for example, a covalent bond between hydrogen gas, H2, between hydrogen and hydrogen, each has 1 valence electron. So they approach each other to share the 2 electrons. And here the sharing will be equal sharing. Equal sharing. مشاركة متساوية. And this one is called non-polar covalent bond. If we take another example, it's like HCl. Hydrogen has 1 valence electron, Cl has 7 valence electrons. So they approach each other, but actually here, as we see, the chlorine is electron rich. So it is formed partial negative charge on chlorine, and hydrogen is poor electron poor. So it is formed partial positive charge, and this then dipole moment will be a dipole moment, and the sharing actually here is not equal. So the shared electrons are closer to the chlorine atom than hydrogen. So this sharing is called an equal sharing. An equal sharing. مشاركة غير متساوية. And the one is called polar covalent bond. Polar covalent bond. In the periodic table, the electronegativity increases across a period from left to right, from left to right, across the period. And decreases down a column. That means from top of the column to the bottom. As we go to the bottom of the column, down the column, it decreases. And also, the electronegativity difference, if it is between 0 and 0.4, the bond will be nonpolar bond. And if it is between 0.4 and 2, it will be polar bond. And if it is greater than 2, it will be ionic bond. Now I talk about bond energies, bond energy, and bond length. I'll explain them both through one example. If we have carbon-carbon, single one, and carbon-carbon, double bond, and carbon-carbon, triple bond, as you see, the single bond is longer than double bond, and double bond is longer than triple bond. So, the shorter bond is stronger bond. So in this topic, I finished now chapter 4 and wish you best of luck.